Want to learn how to calculate the CG of a compound angle wing, or actually I should say the mean aerodynamic chord? Stay tuned and we'll show you how it's done. Welcome to the channel and let's get started. So what I have here is a small UAV, RC drone, FPV kind of aircraft. Show it to you all fancy and rendered. And it has like a reverse crank delta wing shape. A little bit of a Horton tail on it, so it has many different sections to it. And the trick is with the CG, a delta wing or flying wing, basically they're typically balanced at 25% of the mean aerodynamic chord. So how we go about this also works for conventional wing if you're trying to find the mean aerodynamic chord of a wing with multiple tapers or bends to it, as shown here. So what I have it, here's the planform shown from the top, and it's broken into several, let's see here, in top view. I actually have it broken into 4 sections with this little crank area turned into 2 individual sections. So those are shown here, and I turned them into an area so I can get a projected flat area for each one. And I simplified them into basically trapezoids. So the first thing is what I call the zigzag method. It's a geometric way to calculate the mean aerodynamic chord for a tapered wing for a particular section. So let's just say this is the biggest section right here. You would take this tip chord, as shown here, and you would copy it to over here and over here. And this root chord, you copy it from over here to over here. You cross them like so. You draw a line going down it and you trim it to the leading edge and trailing edge. And that would be your mean aerodynamic chord. And then to get the 25% point of that, I basically trim it halfway across, and then I'll get a midpoint measurement, and that gets me from my reference, which is the nose here, 6.33 inches. I've replicated that for all 4 sections. And I have that same reference, like where's the 25% mean aerodynamic chord from basically the leading edge of this section here. So I have that here as 3.4, 2.9, 6.3, and 12.3. And then next thing I wanted to go into, and this is independent of any CAD system. I'm using Rhino here, but this goes to show you how it works in this particular one. Again, AutoCAD or any kind of CAD should be able to do this kind of dimensioning. You can even do it with graph paper if you want to go really old school. Next step is to find the areas. So in Rhino, it's just area. Click on the object, and this one is 80 square inches. Do another one here just for example again, 22.5 inches. So what I've done is I've called these A, B, C, and D sections, going left to right. I have that 25% mean aerodynamic chord detail for each one. Of course, if you're just doing one section, you just stop there and you'd have, you know your mean aerodynamic chord, you know where in space the 25% line is, all that. But this is getting into how do you computate this for a complex shape as shown here. And really the mean aerodynamic chord doesn't matter so much with the delta wing and fly wing. They typically balance right around 25% of mean aerodynamic chord. So the whole goal of this exercise is where do you put your CG for this particular aircraft. If you're using something with a tail, that range might go forward or back by a few percentage points, but this is mostly for tailless aircraft. So we have that 25% reference here as CG, and then you have areas that I showed earlier, how to get the areas. And it's kind of like a weighted average how you do this, and it's called a product and mathematical definition when you take two numbers and you multiply them times each other. So you got this column M here, you go all the way to the bottom, grab all these guys and you sum them. So this is the sum of all that stuff. Then you take the areas, find the total area. Again, that's the sum of these detail areas. And then you go back over here and you take the product and you divide it by the area. What you'll end up with is, this is saying that the 25% line from everything we've shown here is 5.41 back. So we'll get that in the CAD file here real quick. Go over this one and draw a line. And we will move it down by 5.416. There you go. And that is where the CG of this aircraft wants to be. So just throw a little symbol on it. Point. Sure. Extend it. Trim it. Make a little CG symbol here. Just zipping through some fancy commands here. Trim. And then hatch. Hatch boundary. Computer's thinking about something. Oop. Went through things too fast. Okay. Okay. Nope. Group. I'll get those together. Bring it over. And they have like pre-made symbols in some CAD software, but Rhino, it's really quick and easy to just make something like this. Yep. Which commands, I want to copy that. Ortho on, grid snap off. There we go. And there is our CG for this aircraft. Now going into here, now that we have an aerodynamic shape, I have things like the battery, the camera, servos, which I just found that out the other day. 9-ground servo really weighs out to be about a half an ounce when you include the wires and everything. So I got all these various components, and on this particular design, the engines or the motors are going to be where they are. Let's see, move it forward and go perspective. So these motors are going to stay where they are, but this camera has some freedom to move forward or back, along with the battery, servos, a receiver. There's a lot of volume in here, even though it's a small aircraft. It is going to have a small vertical stabilizer. Really no need for a rudder because you got twin engines with a, kind of conventional twin setup. So use differential thrust programmed into the transmitter. But the next piece of the puzzle is in CAD figuring out where these pieces should go to get this thing balanced. As you can see, it has a lot of, compound curves. So this is really set up to be 3D printed in sections. So that's basically the overview. And getting back into it, you just take your trapezoided section, you do geometry as shown, and that'll give you mean aerodynamic chord. And 25% of that chord on a flying wing, if that was just it right there, would be where that CG is. But we have these other sections, and when you do all this math on it, it gives you your 25, basically where 25% of the theoretical M.A.C is. And for a flying wing, that is basically your starting point for a CG. And this is a symmetric airfoil on this, so it really is a number that's worked for a variety of flying wings and delta wings I've done so far, or even ones I've built from plans. So hopefully that'll help you understand, how to do this stuff. It's all basically like Excel and geometry, and that's basically the gist of it. The formulas are fairly simple. So hopefully that makes sense to everyone, and they'll help with your aircraft design project.